Okay, so from chapter 8, we are going to continue with limiting reagent calculations. And then we are going to talk about percent yield and conservation of mass. And then we're going to move on into chapter 13, where we're going to start talking about solutions and solubility. And solutions and solubility will be what we talk about all next week, and solutions in reactions and things like that, and concentration. All right. So for limiting reagent problems, I also ask for theoretical yield a lot of the time, but there will be times when I only ask for the limiting reagent and I don't tell you which product to go to. And in the case where you need to determine a limiting reagent and you don't need to give a theoretical yield, you can choose either product if there's more than one product, but you have to make sure that you convert both of those reagents to the same product. And I'll give you an example of this. If I have 4Si2H3 plus 11O2, which will go to 8SiO2 plus 6H2O, I react 28.2 grams of Si2H3 with 9 grams of O2. What is the limiting reagent? Now, in this case, once again, I didn't tell you which reagent I want you to go to. So choose one and convert both of these amounts to the same reagent, okay? And you have to do that because you have to determine, you have to see which one will produce more. And going to two different products involves a different molar ratio and also a different molar mass. So if you take this amount and you go to H2O and this amount you go to SiO2, it'll be like comparing apples and oranges. You want to compare apples or oranges. So I'm gonna go to H2O. So I go 28.2 grams of Si2H3, and that's 67.16 grams per 1 mole of Si2H3. And if I'm going to H2O, what's my molar ratio here? 6 to 4, 6 moles of H2O to 4 moles of Si2H3. You can stop at moles, but I'm going to go all the way to grams. 18.002 grams per 1 mole of H2O. And that's going to give you 11.3 grams of H2O. But we're not done yet. Yes, Elliot. Because I chose it. Because the way that you determine what the limiting reagent is you determine the yield of the product. And because I didn't specify either product, you can choose either and just make sure you go to both, take both reactants and go to that same product. So now I have to go to 10.9 grams of O2 32.00 grams per 1 mole of O2. So remember that O2, even though it's elemental, there are 2 oxygens, which means the mass is 2 times 16. So our mass is going to be 32 grams per 1 mole of O2. And then our molar ratio is going to be 11 moles of O2 to 6 moles of H2O. And once again, we're going to use 18.02 grams per 1 mole of H2O, which will give us 3.35 grams of H2O. Based on this, did I do something wrong? You are right. Yeah, I just wrote that wrong. Thank you. Okay, but you will still get 3.35 grams. Based on this, what is our limiting reagent? O2, exactly. So in this case, didn't need to find the yield. I mean, didn't need to you didn't need to give me the theoretical yield, but you need to give me the limiting reagent. And if it's the limiting reagent for H2O, it will also be the limiting reagent for SiO2. Okay, so no matter which product you choose, you should get the same answer for what is the limiting reagent. Any questions on that? All right. I would like you to do some practice. 10.8 grams of calcium hydroxide react with 18.0 grams of iron 3 nitrate. What is the LR? First, you have to write out the equation and balance it. What type of reaction does this look like? I heard it whispered. No. You're reacting 2 ionics together? Double displacement. Okay. So it's a double displacement reaction. Write out the reaction, predict the products, make sure all of your compounds are charge balanced, then balance the reaction. Then you can do this calculation. All right? And raise your hand if you need help.
Kenzie, just a heads up that I have to leave at 1 too.
Oh, right, yeah. We won't finish much later than that, so.
Okay.
So you're missing something about these. They're technically balanced, but you need to show that it's still a polygon. So. Otherwise, it's perfect. Now balance the overall equation.
All right, thank you. That's what I thought.
I know. And like a third of my students were missing last night. And I was like, you guys realize this is not a real holiday.
Yeah.
Like people going to hide my class anyway. Like
I was thinking that too. No one went to the CLC yesterday.
all the time. I can smell it when you guys come in high. Like I can't. I know what it smells like. Yeah, like a third of my class was missing last night. So you can pick items, charge balance,
Oh, you're given range of iron nitrate and you're calcium nitrate.
and for both of them, that's what you say. I don't know. It's like, I can't figure out. So I thought that was like no. It just holds the pens. The problem press on one side as you're writing. It would, yeah. This is easier. This is why I do this. It doesn't write like I could if I open, this is also a touch screen. And if I started the meeting here, I could use this, but I start the meeting here, so I write on this. So whoever starts the meeting can actually write. Chart balance. Then it'll be much easier to balance your reaction.
Yeah, just to figure out. Whichever one you can either go. Wait, oh, yeah, so
I didn't know.
this is calcium hydroxide. Yeah, that should be slick. Yeah. You can either go calcium nitrate or iron hydroxide, whichever one. Oh, really? Yeah.
Yes. This summer, I'm going to watch it every single day. I've never seen it.
How ambitious.
When I go back to listen.
Who? Oh.
The whole thing. So
Nope.
you did. I got it from my friend. I want one of them actually. Like they look really great. I have them. No, it just goes long. I don't know.
Like the arm.
It's next week, and I got him his favorite character, but not the favorite, his favorite male character was I'm gonna go and buy the body for Costco,
Nice.
and then I'm gonna keep the case in like a separate birthday bag so his parents don't see it. Because I think they might question just a little bit about what it is. It's so bad. But that's yeah, the view. I've never seen that one.
Really? Me neither. Yeah, like why would I watch that?
I don't know.
How are we doing? Can I go over it? Yes? No? 2 more seconds. Okay. I got a request for 2 more seconds.
Set up.
So this is what your reactions should look like. This is the balance equation for this reaction. Remember, you have to charge balance with the fact that calcium is 2+, iron is 3+, and both nitrate and hydroxide are 1-. I chose to go to the, is that a hand, Paulina? Okay. I chose to go to the product iron hydroxide. If you go to calcium nitrate, that's okay too. You will get the same answer for what is the limiting reagent, but not the same answer for the yield. So I'm going to start with 10.8 grams CaOH2. And I'm going to convert that using the molar mass, which is 74.10 grams per 1 mole of calcium hydroxide. And if I'm going from calcium hydroxide to iron hydroxide, what is my molar ratio? 2 to 3. Yep. 3 moles of calcium hydroxide. Huh?
Isn't it? You said, what are you going to?
I'm going to iron hydroxide.
Oh.
Okay. So it's 2. Yeah, I chose iron hydroxide. So it's 2 to 3. If you went to calcium nitrate, it would be 3 to 3. Calcium hydroxide, 2 moles of iron hydroxide, and that mass is 106.87. And that gives me 10.38 grams. But I'm not done yet because I have to consider the iron nitrate. So 18.0 grams FeNO3. The mass of that is 241.88 grams per 1 mole of iron nitrate. And that's a 2 to 2 ratio. 2 moles of FeOH3 to 2 moles of FeNO3. Sorry, I'm running out of room. 106.87. The great thing about the fact that you're going to the same product is that you only have to do one calculation for the mass of the product. And that gives you 7.95 grams. So what is our limiting reagent? Iron nitrate. You should have gotten that whether you went to calcium nitrate or iron hydroxide. Any questions on that? Okay. Let's talk about percent yield. We've been talking a lot about theoretical yield. Theoretical yield is what scientists do when they put in a certain amount of products, certain amount of reactants, and then they say, okay, this is how much product I should get. But the thing about science is that no experiment is perfect, and nearly every experiment will have some loss of the product, especially if it's a many-step reaction. So one of the calculations that especially synthetic chemists do, and that you will do in 110 if you go ahead in chemistry, is a percent yield calculation. Percent yield is pretty simple in terms of the calculation. So you have actual yield over theoretical yield times 100%. So it's what you actually got over what you should have gotten times 100%. In our last question, if I had asked for theoretical yield of iron hydroxide, the answer would have been 7.95 grams theoretical yield. But someone could have done that reaction and instead gotten 6.85 grams actual yield. So based on that, I can determine my percent yield by just dividing 6.85 grams, my actual, over 7.95 grams, my theoretical, times 100%, which gives me 86.2% yield. Now, in this calculation, we assume that 100% is an exact number. So we count our sig figs as 3 from here, 3 from here. So our answer should have 3 sig figs. Can you have a percent yield that's higher than 100%? You should not. Because we're not alchemists, we're chemists, which means that we can't pull mass out of the air. So in my class, you should never have more than 100% yield. If you have more than 100% yield, you did something wrong. There are a couple of experiments that you can do, especially in, I think, 110, 111, that sometimes you have to dry out the product. And if you don't let it dry enough, there's some leftover water and you can get over 100%. But on my test, you will never get over 100% yield. Okay? So, a question that I would ask on the exam using this reaction again. This is from, I did some of that this reaction from, on Wednesday, whatever day it was. 0.11 grams of aluminum is treated, which just means reacted with, 0.11 grams of Cl2. What is the theoretical yield and limiting reagent? If the actual yield is 0.10 grams, what is the percent yield? So this, I would like you to do this full reaction, so this full question. So once again, we're doing a limiting reagent and theoretical yield. I want you all to have that down really well, which is why I'm making you do a lot of that. And then on top of that, I want you to add the last part, which is the percent yield. Okay, so this is a type of question that I will have on the test. Have at it. What? What?
Yeah.
Limiting reagent.
It looks like
Limiting reagent. There you go. Better? Okay. You had this look of complete confusion.
Yeah. It should be ALCL3 because you're looking for the product. Yeah.
So you can keep it in our names. Gotcha.
Yeah. Go. Yeah. And then on your next one, do the same thing for the
So like do 3 CL or
no, let's go with the second version. It was like the exact same thing.
and then you'll have one AL CL 3 and that's
Yeah.
cool.
Yeah.
You know, during the test source like this.
Yeah.
I'm gonna stand right here. Look up, or I'm like, hello, what's your eye? Take
That would be one more. So there's only one more there. Don't double count your moles. But that first part is more the other way. Yes.
Yeah.
No, No. You're not a
And then do the third part, which is your position.
Because kids were tripping and they jumped off the Pirates of the Caribbean ride.
Oh my God.
They got on the island and started throwing like the treasure and stuff. That's so bad. So they kicked ours.
I would too. I would kick. Yeah.
That was like.
I will never read that. Never ever. Because I don't like feeling falling. Just it's not fun for me. And like just no, like don't want to do it ever.
I think I can't tell what's worse when you're on the tower chair and you're dropping and you feel like you're dropping, or like if you're just on like a top zone and you can't. I remember whenever I was on those places.
There are some rides that they visually they make you think that you're dropping, and so you feel it in your stomach. If you close your eyes, it doesn't feel like you're dropping anymore. Harry Potter and The Simpsons.
That was very specific. She just knew. She's like, yeah.
Also, The Simpsons ride does that too. It like makes you look like you're falling, like The Simpsons ride. So in Universal, so it makes you look like you're falling, but if you close your eyes, you no longer have that feeling because it's a visual simulation that makes you think. So. All right. What is our theoretical yield? Sorry, that's wrong. I wrote the wrong thing. What is our theoretical yield? I did the same thing in class yesterday. What is our theoretical yield? 0.14. So that's our TY. What's our limiting reagent? Cl2, that's our LR. You must label those on your test so I know which is what. You can't just box vote. You have to actually tell me TY or LI or theoretical yield or limiting reagent. Make it clear that you know which is which. And finally, your percent yield should be 0.10 over 0.14 times 100%. That'll give you 2 sig figs, which gives you 71% yield. Any questions?
Wait.
So this is your theoretical yield. This is what you actually got. Oh, okay. That's exact. Yep. Okay. We're gonna do a quick thing on conservation of mass. Yeah. I don't want you to round up. I want you to round properly. If up is proper, then yes. In this case, it was 71.4, so I rounded down. Oh, unless you kept sig figs from your here, let's go back. So I got this question in class yesterday. So since this is an answer, it should have correct sig figs. It should have 2 sig figs. However, if you put this in with extra sig figs here, you might have gotten a slightly different answer. And I will account for keeping extra sig figs in the actual. Okay. So it might have changed your answer here slightly, but you should still end up with 2 sig figs. But yes, always round properly.
Do sig figs matter in that?
They do, yes, because I have, first of all, I have 2 sig figs here. And then I also had 2 sig figures in my answer here. Both of these are 2 sig figs. That gives you 2 sig figs. Conservation of mass. The reason we can predict our theoretical yield is because generally in the reactions we're talking about, we have this thing called conservation of mass, which means mass is neither destroyed nor created. In special circumstances, when you get down to the quantum level and when you're talking about nuclear stuff, you can have mass converted to energy, et cetera, et cetera. But in this case, we just have conservation of mass, which means that the sum of the mass of the products will equal the sum of the mass of the reactants. Sorry. 10.2 grams of CaCO3 decomposes when heated. 5.72 grams of CaO is weighed after. So, and our reaction is CaCO3 decomposes into CaO, O2. If you captured the CO2, what would it weigh? I took a bunch of this. I took 10.2 grams. I heated it, and I ended up getting 5.72 grams of CaO. I want to know how much, if I had actually caught and measured the CO2 that was created in this reaction, how many grams would it be? So what do you think I have to do here? It's really simple. Sum of mass of products equals the sum of the mass of reactants. So our sum of the mass of reactants is 10.2 grams. I have 5.72 grams of CaO, and I need to figure out how many grams of CO2. So what do? Algebra. You subtract 5.72 grams from each side, and X is equal to 4.48 grams of CO2. You could go in and you could convert 10.2 grams of CaCO3 to grams of CO2, but you don't have to. This is a really simple problem in terms of setting it algebraically. What I might do is give you maybe 2 products and 2 reactants, and I'll give you all but one of the products, and you'll have to determine which. But just know that you can always just set it up. Sum of the mass of products equals sum of the mass of reactants, and solve for X. That's all you have to do when it comes to conservation of mass. All right? Excellent. Let's talk about solutions. In salt water, what is the solvent?
Water.
One of two. It's actually water. What is a solute? Salt. Let me write that out better. Solute. A solution has two things. It has a solvent and a solute. Those are multiple solutes, depending on the solution. The solvent is the main component of a solution. And since the solution is a liquid mixture, a solvent is always liquid. A solute is the minor component of the solution, which means there's less of it. And this can be solid, liquid, or gas. So you can have a solid, like salt water. You can have a liquid-liquid solution. For example, any alcohol is generally mostly water with some ethanol in it and other things too. And gas, you can have oxygen dissolved in solution. You can have CO2 dissolved in solution. So yeah, so the solvent has to be liquid, but the solute can be solid, liquid, or gas. Does everybody have this done? Good. So what happens when an ionic compound dissolves? Anybody? What happens when an ionic compound dissolves? What? Separates into its ions. So what happens, for example, in salt water, do you guys remember what this is? Oh, I need to actually put a. See you later. That delta minus and the delta plus, what does that mean? One is slightly more positive than the other. So in water, oxygen is slightly more negative and hydrogen is slightly more positive. So when sodium dissolves, it's going to be attracted to the negative end of water because it's positive. Chloride is going to be attracted to the positive end of water. So as these water molecules are floating around, they're going to try to align themselves so the H is next to the O. And then also the sodium and chloride are going to try to align themselves to where their opposites attract with the water molecules. Now, These dotted lines have names. First, you have the solute attraction. The solute attraction is the attraction, the charge attraction between the Na plus and the Cl minus. The solvent attraction is the intermolecular force of the solvent. Does anybody remember what the intermolecular force in water is? Hydrogen bonding. H and O are attracted to each other. It's called hydrogen bonding. And then you also have the solvent solute attraction, which is the attraction between the ions and the solvent. And we have this solubility chart, right? And some things are soluble and some things are insoluble. And the only way that something can be soluble in water is if the solvent solute attraction is the strongest of these three attractions, right? Because if this isn't strong enough to break up this or this, it's not going to dissolve. So for something to be soluble, the solvent solute attraction must be the strongest. So I might have this diagram and you'll have to label what each of these is. And then you might have to tell me what needs to be the strongest for something to be soluble. Any questions on this? So this is what's happening on the molecular level when something is dissolving. So we have some factors that affect the solubility in addition to just the nature of the solvent and the solute. Temperature and pressure can both affect solubility in a solution. Does everybody have this? Okay. Factors that affect solubility of solids and gases. The first one is temperature. If I heat up water, does that make salt more or less soluble? More, right? Because if you've ever made, a saline wash for, a canker sore or something, you heat up the water. That means you can get more salt to dissolve in the solution. Higher temperature, more soluble. All right. Same with sugar. Sugar is it's not an ionic compound, but it's a molecular compound that has hydrogen bonds that hydrogen bond with water, so it makes it soluble. So for solids, both ionic and molecular, are more soluble at high temperature. So high T, high solubility. For gases, it's the opposite. Gases are less soluble at high temperature. So high T, solubility goes down. So more soluble at low temperature. And if you've ever boiled a pot of water, you've seen this in action. So when you boil H2O, step one, before it actually starts boiling, you see tiny little bubbles of gas. Those tiny little bubbles are not water vapor. That is other gases, atmospheric gases, desolubilizing from the solution as you're heating it up. So you take water, you boil it, and you start seeing tiny little bubbles. Sometimes they're on the bottom of the pot, on the sides. That's desolubilizing N2, O2, CO2, things like that. Atmospheric gas. Step two, when things actually start boiling, that is when you have put in enough heat to induce a phase change in water. So those bubbles, the large bubbles, are actually water vapor. Okay, so step two is you see big bubbles. That's H2O phase change. Sorry, I'm running out of room. Two different steps, two different sets of gases. So next time you boil a pot of water, see if you can first see the atmospheric gases desolubilizing and then the water turning to water vapor. Any questions of that? Another factor that can affect the solubility of gases only, not solids, can anyone think of an example? What? Propane? That's more about the phase, that's not solubility, it's more about it's a liquid at high pressure. But when something that's a gas that's soluble in liquid, and then you release the pressure, we'll talk about that in a couple minutes. But yes, that's one of my examples. I drink carbonated water almost every day in class. Any carbonated beverage, including soda, is an example of this. So when you open a soda can, first step, when it's closed, the company pumps a lot of CO2 or a lot of gas into the top of the can. So the can is highly pressurized. And what this means is that any gas that's soluble in the liquid, any gas that's dissolved in the liquid, basically doesn't have room to come out of the liquid to desolubilize because there's already too many gas molecules stuffed in the top of the can. However, when you release that pressure, there's a lot less of those molecules above the top of the liquid, which means that gas can come out of solution. And that is the CO2 bubbles coming out of solution, okay? And then eventually, all the CO2 that is dissolved in that solution comes out of solution, and we reach an equilibrium, and that's when your soda goes flat. Hannah mentioned the bends. Who here scuba dives? What gas do you have to worry about when it comes to scuba diving? Nitrogen. So at very low depths, you have high pressure. At high pressure, gases are more soluble in your blood. And if you release the pressure too quickly, that is, if you come up to the surface too quickly, if you don't equalize, is it every 10 meters, something like that? 15 meters, there you go. You will get something called the bends, which is basically the gas that was solubilized in your blood at low, at high pressure, comes out of your blood in bubbles. So your blood is basically boiling. You can boil due to temperature, but you can also boil due to pressure. So the bends is when you have gas bubbles in your blood, and it can kill you, and it is very, very painful. It's called the bends because people bend over in pain from that. And then you have to go into a depressurization chamber. And so always equalize your pressure on the way up when you're scuba diving, because you don't want bubbles of gas in your blood. Your face. Any questions on that? That's all I've got for you today. Have a good weekend.